Imagine pulling two distinct espresso shots. You measure the liquid, crunch the numbers, and both return an identical extraction yield of exactly 22. To actually control what ends up in the cup, we have to trace the process backward from the brewed liquid to the raw material. Extraction operates as the inevitable endpoint of a rigorous physical engineering process. It is not a spontaneous chemical event that occurs independently inside your brewer. The structure of the bean undergoes three distinct phases of architectural alteration: cultivation density at the farm, enzymatic processing at the mill, and thermodynamic expansion in the roaster. To master extraction on bar, a professional must discard broad formulas and map the specific physicochemical history of the bean. The baseline physical variable of any coffee is its cultivation density. This metric is directly tied to the altitude of the farm. At higher elevations, cooler temperatures cause the coffee cherries to mature slowly. This prolonged growth phase forces the plant to develop a much tighter, denser cellular structure within the seed. Compared to coffees grown at lower elevations, these high-altitude beans present a formidable physical barrier. Their dense matrix offers significant structural resistance to water penetration. Once harvested, the beans undergo processing. This first post-harvest step shifts the architectural focus from density to cellular permeability. In the natural or dry process, the coffee cherry is left intact while it dries. Over an extended period, enzymes actively degrade the fruit's mucilage layer. This enzymatic breakdown dissolves solid cell wall barriers, leaving the matrix more porous and extractable than heavily washed coffees. Before a bean is ever exposed to heat, its base density and processing-induced microchannels strictly dictate how easily water will eventually penetrate its matrix. Roasting is a violent thermodynamic event. It expands the bean's internal architecture, shattering the dense green seed into a porous, brittle structure. We can model this using multi-phase flow. Inside the cell, three distinct phases interact under extreme heat: the solid cellulose structural walls, pockets of liquid water, and expanding trapped gases. As thermal energy is applied, that liquid water continuously evaporates. This phase change converts the liquid into water vapor, generating intense internal gas pressure that pushes outward against the cell walls. This entire process is driven by a drying front, a specific thermal wave traveling inward from the exterior crust of the bean directly toward the raw core. Directly ahead of this advancing drying front, a localized zone of extreme gas buildup forms. We call this the vapor pressure ridge. The intense expansion fractures the cellulose structure, leaving behind rigid, open nanopores, the essential physical pathways for flavor release. Pushing a roast darker increases this physical porosity, making the bean easier to extract. However, the prolonged heat simultaneously burns off the soluble aromatic mass that gives the coffee its unique character. The roaster's true mechanical function is locking in the bean's final nanoporous structure without degrading its volatile inventory. The physical engineering concludes in the roastery, but the brew phase initiates in the cafe with the mechanical action of the Berg grinder. Every coffee possesses a distinct fragmentation profile. This dictates how uniquely structured beans shatter differently under the exact same mechanical stress. This chart compares particle size distributions. When a highly dense, brittle Ethiopian bean and a softer, lower-density Brazilian bean enter the exact same Berg gap, they produce entirely different curves. The curve representing the Ethiopian bean spikes significantly higher on the left side. Its inherent brittleness generates a massive volume of microscopic fines, radically increasing the total reactive surface area. This sudden influx of fines strictly alters the multi-phase fluid flow of water as it passes through the compressed espresso puck. These fines are a double-edged sword. They massively accelerate the speed of extraction, but they exponentially increase the risk of physical channeling and localized over-extraction. Relying on macroscopic grinder settings is an illusion. An identical Berg gap produces vastly different physical realities in the basket, depending entirely on a bean's inherent brittleness. Once the particles are fractured, we move to chemical dissolution, which is driven entirely by the thermodynamic energy of the brew water. There is a persistent misconception that water temperature simply speeds up the overall extraction rate. In practice, temperature selectively determines which specific compounds are actually capable of dissolving. Highly soluble polar compounds, like simple acids, extract easily at lower temperatures. Stubborn nonpolar compounds, such as complex lipids and heavy aromas, require significantly more thermal energy to mobilize. This graph illustrates the predictive density model developed by Pete Licata. As bean density on the x-axis increases, there is a clear, direct upward correlation with the required water temperature on the y-axis. For extremely dense beans, reaching up to nearly 5 grams per centiliter, the curve hits the top right. You must push the water temperature to a near boiling 211 degrees Fahrenheit to successfully extract those highly desirable nonpolar molecules. Failing to reach this specific thermal threshold leaves a dense bean chronically sour. The water lacks the required energy to penetrate the matrix, meaning only the easily accessible polar acids make it into the cup. Brew temperature functions as a thermodynamic threshold, providing the energy necessary to dissolve the specific complex compounds shielded by the bean's density. This brings us back to the opening paradox. Consider a blend combining a high-density washed Ethiopian seed with a lower-density natural Brazilian seed. When we apply the mechanics of fragmentation, the Ethiopian component shatters into restrictive fines under the burrs, while the Brazilian does not. This instantly destabilizes the physical flow of the puck. Following the constraints of permeability, water rapidly strips the natural Brazilian's open microchannels. Meanwhile, the dense, washed Ethiopian matrix requires significantly more contact time. Finally, under thermodynamic limits, the near-boiling water required to extract sweetness from the dense Ethiopian will concurrently burn and over-extract the porous Brazilian. Blending coffees of conflicting microstructures does not create harmony. It guarantees an unoptimized, compromised weighted average in the cup. True extraction mastery requires completely abandoning macroscopic heuristics in favor of individual component testing. Professionals must isolate their coffees. You must align processing types, fragmentation profiles, and required thermodynamic thresholds long before attempting to combine them in a blend. Exceptional coffee is achieved when the barista respects the precise physical architecture engineered at the farm and finalized in the roastery.